All right, and just as a warning, if you are interested, it is now recording. So if you speak out loud, it will be recorded, and I can send the video clips to parents and tell them this was your child in my classroom. So all of those, you like to cuss me out every day, Giselle, so please don't. All right, so we're looking at lecture 25. All right. Now, lecture 25 is we're going to look at the graphs, the graphs of sine and cosine. And we're talking about parent graphs. And then, of course, we're going to move them around a little bit as well. So you will see over there on the board, we see the parent graphs. I referred to this numerous times with quadratics or square roots or absolute values. If you look at the very bottom, there's three at the bottom, sine, cosine, and tangent. We're going to spend a little bit of time on sine and cosine. I'm going to make some applications to tangent, but we're not really going to discuss it a lot. Okay, so more likely just the sine and cosine. Today we're going to look at just the sine. So capital letter or Roman number 1, we would say the sine graph. All right, so let's just get right into it and let's just do the graph. Okay, so normally when we start doing parent graphs, if you're stuck, you have no idea where to start, always start with the table. Okay, so let's make a table. We'll call this theta, and we'll call this the sine of theta. You know, normally we do x and f of x. Now we'll do theta and sine of theta. And there's 4 key points on the unit circle. Okay, actually 5. We're going to use 5 key points. Where are those 5 key points? I'll give you a hint. We call them quadrantals. I'll give you a hint. Second hint. The first one's 0. What would the next one be?
15. Oh.
No. I thought I heard it.
1.
Not 1.
9.
Okay, give me radians.
Oh. Pi over 2.
Pi over 2. Pi over 2. Okay? And then give me the third one.
Pi.
Pi. All right, and the fourth one?
Pi over 2.
I think I heard it. 3 pi over 2. And then, of course, to bring it back to full circle, we have 2 pi. So we have, if you will, 4 spaces. The space between 0 and pi over 2, we call that quadrant 1. The space between pi over 2 and pi, we call that quadrant 2, and so forth. Okay? So what is the sine of 0? 0. Outstanding. What is the sine of pi over 2?
90.
Yes, at 90 degrees, what's the sine?
0.
I think I heard it. 1. Okay? What's the sine of pi? 0. What's the sine of 3 pi over 2? Negative 1. And of course we come back to full circle, so the sine of 2 pi would also be the same as 0, so that's 0. Okay? All right, now, by the way, in a little bit I'm going to tell you the way to graph any sine or cosine graph is to get 5 key points. These are those 5 key points. All right? Let's look at the graph of it. Okay? So in your paper, we're going to draw something like this. It's kind of like a table, but laid on its side. Obviously, this here is going to be 0. And then let's put 4 equal marks. So if I want 4 equal marks, if you simply put a point out here, cut it in half, and cut both of those in half, you can kind of eyeball it pretty closely. So these are going to be my theta values. So 0, this is going to be pi over 2. This is going to be pi. This will be 3 pi over 2. And this will be 2 pi. Okay. So we have our theta values are my x values, x-axis. Does that kind of make sense? We good so far? Now, just a thought, because we're going to put this on a graph, correct? on an XY axis, what is the approximate value of pi? 3.14. So, what'd you say? 180. Well, we're so used to radians. So if I have a graph 1, 2, 3, 4, pi is actually about
Right, like a little bit.
About right there.
3 pi over 2.
okay. Where would pi over 2 be? What's the decimal value of pi over 2?
The decimal value?
So pi divided by 2. So 3.14 divided by 2.
So it's like, was that less than 1?
Say it again?
Is that less than 1?
No, it's not less than 1.
It's
It's
like
like
1.5.
It's like a little over 1.
It's about 1.57. It's about right here. So pi over 2. So I just want you to understand, on our graph, I'm just going to mark them because they're nice and easy to see. But if we actually have a graph with 1, 2, 3, 4, 5, that's where they would fit in. Okay? Does that kind of make sense?
Yeah.
All right. So let's go ahead and graph our points. We have 0, 0, so that's easy to graph. We have pi over 2 goes up to 1. So if this is actually 1.5, 1 would be about right there. Let's try and eyeball where 1 would be. About right there. All right, so pi over 2 to 1. Okay. Pi is going to be 0. Excuse me. 3 pi over 2 is going to be negative 1. And then 2 pi is back to 0. While you guys are finishing that, I'll fix my boo-boos. Oops. 2 and back to red. Now, if we connect those dots, you'll see the sine curve. And I did this morning, and a student said, oh, it's the sine waves. That's exactly right. There's one sine wave.
That's unique.
Say it again.
That's unique.
That's unique. And just so, I'm going to erase this in a second, but if you want to jot it down or just at least see it, I'm going to put it in green and then I'm going to erase it. But then between 0 and pi over 2, this is considered quadrant 1. Between pi over 2 and pi, this is considered quadrant 2. Quadrant 3 and quadrant 4. And you can see in quadrant 1 and 2, the sign is positive. It's above the x-axis. In quadrant 3 and 4, the sign is negative. It's below the x-axis. So kind of interesting connection between the unit circle and the graph. And honestly, whenever someone ever asks me, like, what's the sign of pi over 2, I never think about the unit circle. I think about the graph. Oh, pi over 2 goes up, so it's 1. 0, negative 1. I always think of the graph instead of the unit circle. They are connected directly. Okay. All right, let's get rid of those things. Oops. All right. Any questions on that graph? How we got it? Because now we're going to play with it a little bit and talk about its characteristics. All right. So we do remember, though, that this does go forever in both directions. Okay, this sine curve is not just one isolated spot. It's actually over and over and over and over and over and over again. And it goes on forever. Okay?
So
Yes.
would we go back to 0 and then go back up to 1?
Yes.
And then 0 again and, I mean,
Yes.
negative 1.
So if I went one more spot,
Stop.
that'd be 2 pi plus pi over 2.
So it'd be back at 1?
It'd be 5 pi over 2. It would be back up to 1.
And then back down to 0.
Back down to 0. And we just
Okay.
keep going in that pattern.
So 0, 1, 0, negative 1.
Now, you're hitting on something that's kind of important. Let's go to this. 0 right here is one of our x-intercepts, right?
Mm-hmm.
Okay, and we're going to give you a different line for x-intercepts, but for right now, that's what we're going to call it. What will we call this one? We say it keeps going back to 1. That's going to be what point? On this particular graph, what would we call that point? Give you a hint, it's the highest. Maximum. Okay? So what would pi be? It would be another x-intercept. Okay? What would this point here be?
Minimum.
Minimum. Everyone knew that one.
And then x-intercept.
And then x-intercept. Another x-intercept. And it's actually returning right back to itself. Now, that's the 5 key points we want to find. Okay, we want to find the x-intercept, if you will. It's actually a midline, but we'll call it x-intercept for now. Of the maximum, where it goes back to, this minimum, and where it goes back to. Those 5 key points. When we can find those, we can graph any particular function. Okay, so what are some other characteristics? Besides it going on forever, besides it's going up to 1 and down to -1 and back up to 1 and down to -1 and back and forth, what else can you tell me? What's the other characteristic of this particular graph? We'll put these in blue. These are important. And on my notes, I just simply put characteristics. And you can put the things we just did. It oscillates, goes up and out, up and out, up and down. Okay. What are some other characteristics of this? Like, for instance, what is its domain? Say it again. Yeah, absolutely. You could say infinity to negative infinity, or we could say all reals. Or you could say negative to positive infinity. Yeah, there's nothing you can't take the sine or cosine of. Okay. All right, so then another characteristic, what's its range?
It doesn't really go past 1.
Say it
It
again.
doesn't really go past 1. It doesn't.
Very good, so that's the range. Exactly right.
One
It's
negative
from
one.
-1 to 1. It doesn't go past either one of them. So if I tell you that sine of theta equals 5.3, you can look at me and say, you're an idiot, because that's not possible. Don't actually call people an idiot, that's rude. Say, no, you're mistaken. That's the nice way to say you're an idiot. I'm just kidding. Say what?
How?
She just
Why
called
would
me an
I ever do
idiot.
that? It's so
Why would
rude.
she do that?
Exactly, they're so rude.
That's so rude. I can't imagine Giselle ever calling someone a name or being a bully. All right, so that's my first 2 characteristics. What's the third one? This one you may not have ever heard of. Okay. Okay, so we call this, so it starts here, it goes to its maximum, it comes back, it returns, it goes down to its minimum, it comes back and returns, and then it starts to repeat, correct? Okay, so from here to here, we call that a period. So it has a period of 2 pi.
When you like say that it keeps going, would you not count to 0? You say it goes to its maximum and then down to its minimum. You don't stop at the 0.
Correct. I mean, there is a value, pi equals 0, but the thing is, okay, here's another characteristic. What's happening here? The function's increasing, right? What's happening here? So even though it hits 0, it's decreasing, so it keeps going
Under
down.
0.
And then it comes back to increasing. It goes back to decreasing. So even though it hits 0, where is it headed? So it's headed down here, it's headed up here. So every 2 pi, it's going to repeat. Okay? So we drew it over earlier, 5 pi over 2, 3 pi, 3 pi or 7 pi over 2, 4 pi. It's just going to keep recycling over and over and over. Just keep adding that on. Same thing this way. Okay? Negative pi over 2, negative pi, and so on. So there's a period of 2 pi. Okay, let's see one other thing. Oh, this one I don't know if you would have thought of, but this is an odd function. Do you remember a long time ago, I can't remember what class you would have heard it, what exactly is an odd function? I know you heard it last year with me, Jaya, and I know I talked about it in college algebra. Do you remember what an odd, even and odd functions are?
Functions, I know what you're talking about, but I don't remember how to.
I think we talked about them last year a little bit.
I feel like I kind of remember.
Okay. So An even function is like a quadratic. It is symmetrical over the y-axis, it reflects.
And the other one is like the S.
And what?
The odd, wouldn't the odd be the S one?
Correct. The odd is kind of like a cubic function, where if I take it and I spin it 180 degrees, rotate, in geometry you talk about rotationally symmetrical, so if I take it and I turn it 180 degrees, it looks exactly the same. Well, if I take this function and I turn it 180 degrees, it's going to be right on top of itself. So it's an odd function. All right, let me see where I'm at. Let's see, we talked about the key parts, right? And this is going to help us with the transformations. We talked about its period. We talked about, oh, one other thing we got to talk about. Well, no, we're going to save that for later. And then it breaks into 4 equal parts, the 4 quadrants. So I think we're good. All right, if there's no questions, we're ready to go to Roman numeral 2. Are you ready? Here we go, Roman numeral 2. All right, this is actually going to be an equation. Y equals A sine of B x minus C plus D. Okay?
You're bored.
Relax, right there. It's very sensitive. I've asked to see if we can turn down the sensitivity thing, but you walk by it or something. Or I found out if my shirt tail hits it, it does weird things.
When you walk away like towards like that table right there, it turns off.
Oh, really?
With the pen, I think.
Oh yeah, it turns off. It keeps going off.
It happens every time you're not
It
looking.
does.
Yeah, I
And then
believe
turn
you.
back, then you turn back around and then.
You know
And
how-
it goes right back when he turns around.
You know how that little pin comes on that annoys me to death? I tried to get it to come on the other day, and Mr. Murray, the tech guy, was in here helping me. I couldn't get it to come on. Whenever someone's here looking at it, it never messes up. But now I have it.
When you look down at your notebook, it turns off. And
Every
I was gonna
time?
say something, but you went back to look at it and it turned on.
All right. All right, here we go. A. Whoops. So A. Hey, so when we had quadratics, what did the A tell us? What'd you say? No.
It was all real?
No, you're not following me. If we had a quadratic, we had y equals ax squared plus bx plus c. What did that a tell us? Say it again. Okay, if it's up or down, and what else? What did you say?
Maximum or minimum?
Not maximum or minimum. It tells us if it has a maximum or minimum. Well, it's either positive, it goes up, negative, it goes down. That's either a maximum or minimum. Okay. Do you remember what else it told us?
How wider?
How wide or how narrow it got, right? This A tells us kind of the same thing. This A is actually, it stands for amplitude. This is gonna, the A out front is gonna tell us how high and how high above and how high below we're gonna go, okay? So, let's say, here is my function, and it goes, rather than up to 1, maybe it goes up to 2 and down to -2. Maybe the A is 2, it's gonna go up and down by a different amount. It tells us how far up and how far down. Okay, so if A equals 2, it tells us it goes 2 above and 2 below.
So like the period?
Say it again?
So like the period, kind of?
The range. Rather than going up to 1 and -1, it would go up to 2 and -2. It just tells us how far above and below it's gonna go. All right, so the first one is the amplitude. How far above and below that's going to go. All right. Part B. B. B is going to be the period. We're going to find it, or how often it goes. So we're going to take, it's actually helps us find the period. Now, a couple things. The parent function, what is the period of a parent function? No.
Point at the top.
How far before it comes back to itself, before it starts to
So
repeat?
like it's like circle, it's 360 kind of,
Yes, so it goes from 0 to what? Give me radians, not 360, not degrees.
2 pi.
2 pi. So it goes from 0 to 2 pi. Its period is 2 pi. In fact, I'm pretty sure we wrote it right there. Its period is 2 pi. Okay, so if b is the period, we're going to take 2 pi. This is another rule. If it's in with the x, if it's inside the parentheses, we always do the opposite. So this is being multiplied, so what do you suppose we're going to do? We're going to divide. So if I take 2 pi divided by b, that will tell me what its period is. Okay, that will tell me how far I go, how long it takes to go all the way up, all the way down, and back to where it started. Okay. All right. I think C we're not going to talk about. C is actually the horizontal shift. How far it moves left to right. We're not going to, I don't think we do a lot with horizontal shifts just yet. We should. But. Oh yeah, we do them later on, phase shifts. Okay, that's your horizontal shift. And then D, I'm going to introduce a new vocab word for you. D,
Amplitude was new.
you haven't heard amplitude before?
I think of planes when I heard that word, but I always thought the right word.
Oh. Okay, so it's the vertical shift, and what we're moving is the midline. I think I said that a little bit earlier. We can do a replay and see if I said it earlier. It's the midline. So normally in a parent function, it's the x-axis. But I can take that midline and I can move it up 2 or down 5 or move it up or down. Kind of like we did the vertical or the horizontal asymptotes. Okay, we can move the midline to different places. Okay. And then that'll just shift everything up or shift everything down. Your amplitude is still how far above and below that midline are you going.
So would your amplitude equal to the vertical shift? Would those be the same?
Not really. Let's give you an example. Let's say I had y equals, let's say, 3 times the sine of x plus 2. Okay? So it's something very basic. It's the same period. The period hasn't changed. It doesn't change horizontally. All I'm going to do is shift the midline and the amplitude. Okay? So if I have my graph, whoops. So if I have my graph, there's my x-intercept, but it shifted up 2 units, right? So my midline is now going to be up here.
So if it was 2, it would go to 4? If it moved like about 2?
Say it again.
If our amplitude is 2 and then the vertical shift went up 2, it would be 4.
It would go from 4 to 0. But since here my amplitude is 3, now it's going to go up to what? Up to where? If this is y equals 2, it's going up to 5, and it's going to go down to,
-3?
no, because remember starting at 2, so it's going to go down to 1, 2, down to -1. So if 2 is my midline, and it has an amplitude of 3, I'm going to go up to 5, down to -1. And it's going to oscillate between those two.
So basically that's the x now.
This is now your x-intercept. This is now your x-axis, and you shift up and down. That's your, but we can't call it the x-intercept because it's actually here. So we would call it the midline. So what does that alter then? Okay. Say it again. Not the period, because we haven't changed the period at all.
Horizontal shift.
What'd you say? Range. Changes the range. So now what's the range?
5.
-1 to 5. Because now I'm going from -1 is my minimum, 5 is my maximum, I'm just fluctuating between those 2 points. That's what the A and the D does. Hard part's the period, we'll get to that next. Boy, that's really bad, isn't it? Because that's down 3 and that's like up 1. Should be up to here. Ooh, that's bad.
Wait, will you leave that up?
I'm actually gonna back up a little bit. All right, so we need to talk about the fascia, or the period. Because that's generally the most confusing part.
Who made that?
Say it again?
A tissue. Who
Tissue.
made that?
I don't need a tissue.
No, do you have one?
No, I do not.
That's not what I said.
He said, he says tissue.
I have a
tissue.
sleeve.
Shut up,
if you
I
want
was
to use it.
live.
I'd be booger with those.
Well, I have like
Tissue
paper
is
towels
tissue,
over
yeah.
there.
Mr. Bell.
I'm sorry, I bought some Kleenexes, but I can't buy them
Mr.
all.
Phillips.
Are we good?
Mr. Fi-
She has a question.
Who has a question?
Who made that?
Who made what?
The thing.
This thing here? One of my Algebra 2 students.
Shut up.
That's kind of
Sorry.
nice.
Okay, I have to tell you, are you finished?
Yeah.
Okay, I have to tell you, real quick, the other day I had this, it was like here, and it was touching the screen, so I couldn't do anything on my computer. I was getting so mad, like, why is the mouse not working? But the mouse was like stuck to that spot because this little guy right here. That's how sensitive it is, a little piece of paper.
What is it
touches it.
supposed to be?
It's pretty cute.
I don't ask questions, I just put it hanging on the wall. Okay. Let's see here, I didn't want to do that. Back up and add. Okay. So let's do one. Let's give you some examples. Let's say we have, this is going to be an easy one. Let's just do a real easy one, and this one I'll actually draw it out correctly, so it's not like the messed up last one. Let's give you y equals 2 sine of x. Okay. So what's the only thing that's changed?
There's no D.
There's no d, so the midline is still at the x-intercept. I haven't shifted up or down. Okay. So what's the only thing that has changed? The amplitude. Okay, so let's sketch our graph. Make your
God damn, Ezra's playing.
language 4 spots.
Ezra's sending me reels. Have to pay attention to files.
We know it's going to be 0. We know it's going to be pi over 2, pi, so forth. 3 pi over 2, and 2 pi. Because my period hasn't changed. Nothing inside has changed. My midline is still at 0. So I'm still going to have 0. But now the amplitude causes it to not go up to 1, but the amplitude causes it to go up to 2. So it goes up to 2. It still comes back down to 0. How far down does it go though? It's supposed to go to -1, but since the amplitude is 2, now it goes down to -2. And then it returns back to 0. So we have our curve. I'm trying to draw it as close as I can, but. And all we've done now is we've stretched the sine curve. We've made it wider. All the characteristics are the same. The domain is still all reals. In this case, though, what is the range?
2, -2.
Okay, always do the bottom first.
-2, 2.
So -2 to 2. Notice there's brackets behind it. Nothing else has changed. The period is still 2 pi. The still an odd function. Yes.
Why is it brackets instead of parentheses?
That's a great question. Could someone tell me why I do brackets rather than
It's
parentheses?
just not a function.
I'm sorry?
What if it's not like?
No, it is a function. What's that?
Oh, because that's what it's confined to.
Can I ever have a value?
Because
Oh.
it's not an ordered pair. Like,
Let's
it's
go
not-
back to here. Do I ever have a value where the sine of that value is exactly 1. Yes. The sine of pi over 2 does equal 1. Okay? So in this case, if I were to give you pi over 2, it would actually equal 2. Okay, remember what does the parentheses represent?
It's a decimal point.
Say it again.
That's, or not, sorry, it's like a point on the graph. That's what the parentheses are.
So the parentheses tell me I'm getting closer to 2, but I never actually get there. 2 is not included in my answer.
So brackets.
But in this case, 2 is included because 2 times the sine of pi over 2 equals 2. So because I actually have a value, I put a bracket.
So bracket is concluded and then parentheses is not there, not.
Correct. I'm getting closer to 2, but never actually get to that value. All right, so the range, and the range for all sine and cosine will always be bracketed. All right, you ready for one a little more difficult? This will be the last one before Maya leaves. Here we go. Example. All right, so now we're going to give you y equals 2 times the sine of 3x. 2 times the sine of 3x. So examining it, what has changed? What letters have changed?
X.
Okay, so A and, not C, but B. Remember, C is when you add or subtract. B is when you multiply. So the A has changed, the amplitude.
Wait, how did A change?
It's 2.
Oh, I thought you were talking about compared to the
From the
other
parent.
question.
From the parent graph. It's not the last one we did, from the parent graph. Okay? And then the B has changed. Because the B is now 3. Now here's what that means, just in case you're wondering. Okay? And you're all wondering, in fact you're on the edge of your seat wondering, what exactly does that 3 mean? Okay? So forgive my sketch here. What that means is between 0 and 2 pi, which normally, how many periods do we do between 0 and 2 pi? Normally it's 1, correct? But because I have 3 in there, now I'm going to do 3 periods in that amount of space. So it's going to go up and down, up and down, up and down, and back to 2 pi. Okay? So what I've done then is I've taken my sine wave and I've squeezed it together. It's going to go up and down much faster. Okay? Don't fall asleep on me.
So when it's just X, like you go once, and then if it's like a number, you go like that many times.
Correct. Correct. So if it was 5, it would go
1,
up and down 5 times inside that space.
Of the 5 points.
Between 0 and 2 pi, correct. Now, how do we graph that?
I'm not sure.
All right, so here we go. Pay attention. Remember, what did we say the period equals?
2 pi
pi.
divided by B.
2 pi over 3. Because 2 pi over b, and since b is 3, it's 2 pi over 3. Okay? So, here we go. Here's the fun part. If you've fallen asleep, stand up. Stay awake, this is important. Just kind of the crest, if you will, the climax of today. Climax of today. All right, here we go. Go ahead and sketch your graph. Now we know we're going to go up to 2, correct? And we're going to go down to -2. Okay? And we know we're going to go 1 full period, so I'm just going to go out here and put a mark there. However, normally that mark is 2 pi, correct? This time though, what is it? We're going to put 1 period on here.
So it's going to be pi over 2 again. 2
2
pi
pi over
over
3.
3.
Because normally, remember, it's 2 pi. I go up and down within 2 pi. But now I'm doing 3 of them, so 1 period is going to be 2 pi divided by 3. Okay? Does that kind of make sense? Yes? No? What part, where did I lose you?
If in the parentheses it's just x, it's just 2 pi, and then whatever number, if there's a number in between, like with the x, is 2 pi divided by that number.
Correct. And see how we've been drawing 2 pi on the end of all of them?
It's just 2 pi between and then over the number.
2 pi?
Numbers in between.
Well, I'm changing that point. I'm changing where it ends. It's going to do one full cycle, but rather than taking 2 pi to get there, 360 degrees, it's going to happen in 2 pi over 3. It's going to happen at 120 degrees. It's going to happen much sooner. Okay? So then, remember what I said to put the dots? I said put a mark here. That's the reason why. That's where your period is going to go. 2 pi divided by 3. So then I said cut it in half. Okay, so what's half of 2 pi over 3?
60.
Say it again.
60.
60. Okay, because it's 120. So what's half of 120? 60. So what's 60 in radians? Pi over 3. And you know that kind of makes sense. If you have 2 pi's over 3 and you want half of it, that would just be 1 pi over 3. That does kind of make sense. Okay? What's going to be half of pi over 3? Pi over 6. And what's going to be right here?
This just got way more complicated.
Say what?
This just got way more complicated.
We're dealing with fractions, it's going to. If you like to put it in degrees to help you out a bit, we know this is going to be 120. We know this is going to be 60. This is going to be 30 because it's half. What's going to be in there?
So,
90. Because it's halfway between 60 and 120, right? And that's going to be what? Not pi. Pi over 2.
What you said first.
Pi over 2. So if it does help for now, think of the degrees, but eventually I simply want you to do the radians. Or eventually do the radians. And now you just have to graph it. We graphed it exactly the same way. Where is the, where do we start? We start at 0. At pi over 6, what value is it at? How high does it go?
1.
Goes up to 2. At pi over 3, what's it come back to?
1.
Negative 2?
No. Pi over 3,
Oh, back to 0?
back to 0. Pi over 2,
And then down to negative.
negative 2, back to 0. And there's my curve. And that would do that 3 times within 2 pi.
So the domain is all reals,
Domain is always all reals.
and then the range is negative 2, 2.
Yeah. And your period is 2 pi over 3. That's it. And the only thing we haven't done is shifting it left to right, which we'll do that later. You got it?
Yeah.
Fantastic. Anybody else? Questions? All right, I'm gonna give you a couple practice problems, turn you loose for a little bit. We'll do phase shifts and cosines. Because cosines work exactly the same way. Just has different points on
Bye,
it.
Philip. See you next week.
Have a good one. Okay. All right, so try these problems. Try a couple on your own. You try. We'll do a couple that are kind of basic, and then a third one that's going to be a little bit more of a challenge. Let me see if I can find them on my sheet. Here we go. Oh my goodness. This will be good. Number 1. Try y equals 3 times the sine of 2x. Then I want you to try. It happened, didn't it? Then I want you to try number 2, y equals, let's go with 5 times the sine of 4x. Then a little bit of a challenge one. And be ready, some of you, I'm going to have you come to the board and try these. Where's my challenge one? Oh, yeah, here we go. Let's go with
Oh, not the, oh, yeah.
y equals, what was the what?
Oh, yeah, it's like, okay.
Oh yeah, I got this. 2, oh, you're gonna love this one. 2 times the sine of 1/2 x. Just when you thought we couldn't have more fractions, we add more fractions. 1/2 x. Same rules apply. Everything we did is exactly the same. Try those 3. And if there's anyone who would like to just, hey, I really would like to do this one on the board, I'm glad to let you.
Can I go to the restroom?
Yes, please.
It's not like